Welcome to section 3.2, where we are first going to study subspaces of Rn, and then we will also talk about a variety of concepts like redundancy, basis, linear independence, and span. So first, the definition. A subset W of the vector space Rn is called a subspace of Rn if the following two properties happen. Before I read the two properties and talk about them, we may want to say what a subset is here, because we see that it's different from a subspace. So a subset is any group of objects that is smaller or equal to another group of objects. So if we look at all the vectors in Rn, a subset would just be a group of some of these vectors in Rn with no rule whatsoever, except that all the vectors here should also be vectors in Rn. A subspace is a subset, so it's a group of vectors from Rn, but there are two additional rules. One of which is that you must have the zero vector in the subspace, and the other one is that this subspace is closed under linear combination. Closed under linear combination means that if you have a certain vector, let's call it v, in the subspace, then any multiplication of v by a scalar, so any vector kv, is also in the subspace. Secondly, if you have two vectors in the subspace, v1 and v2, then you can add them together, and the sum will also be in the subspace. These two rules here can be combined into one rule by saying if v1 and v2 are in W, then k times v1 plus L times v2 is in W, where k and L would be real numbers. So you can work on it separately or put both of these conditions together. So, with that said, we can go back to what we've learned last class and specify that the kernel of A, for a matrix of a linear transformation, that kernel is a subspace of Rm, and the image of A is a subspace of Rn. First question, is W, which is composed of all vectors in R2, vectors x, y, such that x and y are both greater or equal to 0, is that a subspace of R2? So we are looking at all vectors that starting at the origin point in this purple area, purple region here. Firstly, it's a subset, of course, because all these vectors are vectors of R2. The first requirement is that 0 is in W, and yes it is, because x and y are both equal to be 0, so the vector 0, 0 is in W. Secondly, can we pick a vector in W, multiply it by any real number, and still have a vector that is in W? And the answer here is no. If you choose vector v here, but you choose k equals -2, the vector -2v now points out of the region. So W is not a subspace of R2. It's a subset of R2 because it has a group of vectors, but it doesn't qualify to being a subspace. In fact, the only subspaces of R2 are R2 itself, any line through the origin, and the vector 0 alone. For any line through the origin, we can convince ourselves, because it goes through the origin, that 0 is on the line, and that for any vector, if I multiply it by a scalar, I will remain on the line. Lastly, the set, the subspace that is composed of the vector 0 alone, also satisfies these two conditions. 0 is in it, obviously, it's right there, and if I multiply by a real number k, I will still get 0, which is in the subspace. We can extend this idea to Rn, for example, for R3, so the three-dimensional space. The subspaces are R3 itself, any plane through the origin, any line through the origin, and the vector 0 alone. So the additional here thing is any plane through the origin. If we have two vectors that define a plane, then we can add them together. We will remain in the plane. We can multiply one by a scalar and we will remain in the plane. And of course 0 is in the plane as well. This should read any plane through the origin. Now we're switching gears and we're looking at the span. So consider the matrix A given here. Two questions. First, find vectors in R3 that span the image of A, and secondly, find the smallest number of vectors that span the image of A. Before that, let's look at an example of the image just as a refresher. If we pick a random vector in R4, the vector 1, 0, negative 1, 0, we can proceed to doing A times that vector x. So A times 1, 0, negative 1, 0 gives negative 1, negative 1, negative 1. You can check quickly. What that means is that the vector negative 1, negative 1, negative 1 is in the image of A, right? Because we can reach it using a certain vector in the original space. Now we've seen last class that to find the image of A, all we need is to use the column vectors. Right, so we know that the image of A is spanned by 1, 1, 1, 1, 4, 3, 2, 2, 2, and 2, 5, 4. The columns of A always span the image. So this is great, and we know that because if we take the base vectors, the standard base vectors 1, 0, 0, 0, and then 0, 1, 0, 0, and then 0, 0, 1, 0, and finally 0, 0, 0, 1, and we do A times these standard basis vectors, we will get 1, 1, 1, the first column, we will get 1, 4, 3, the second column, etc., the third and the fourth column. Now, any vector, any four-dimensional vector, let's say 5, 7, 9, minus 2, is a linear combination of this one, and the other standard basis vector. I said 5, 7, 9, negative 2, I think, so it's 5 times this vector, plus 7 times that vector, plus 9 times the other one, minus 2 times the last one. So because of that, we know that whatever happens with the image, it's always going to be a linear combination of 1, 1, 1, 1, 4, 3, 2, 2, 2, and 2, 5, 4. However, this is not the least number of vectors we would need to define the span of the image. Firstly, which is quite easy, we can notice that the vector 2, 2, 2 is not useful because we already know that the vector 1, 1, 1 is in the image. So we would know that by multiplying this one by 2, we would actually get this vector. So this third column doesn't give us any new information about the image. It doesn't give us new vectors that are in the image. It's a little bit harder to see, but the fourth column is also useless, and we will call that redundant. Because if I know that 1, 1, 1 and 1, 4, 3 are in the image, then the sum of these two vectors is also in the image, 2, 5, 4, which is exactly the fourth column. So the fourth column is also not needed to define the span of the image. So we are left with the first two columns. Clearly they are both necessary because with 1, 1, 1 I would never be able to multiply by a scalar and get 1, 4, 3 obviously. So these two are necessary. So in conclusion, we can say that the image of A is the span of 1, 1, 1 and 1, 4, 3. This is not incorrect here, but they are redundant information. This is the shortest span we can get. You may wonder, would I be allowed to say that the image of A is the span of 2, 2, 2, 1, 4, 3, for example? And the answer is yes, of course. If we include 2, 2, 2 in the span, then we could say that 1, 1, 1 is redundant, if you want. We could also say that the image of A is the span of 2, 2, 2 and 2, 5, 4. Because if I have 2, 2, 2 and 2, 5, 4, then with linear combination I could reach 1, 4, 3 and 1, 1, 1. We typically, though, would take columns in order, and we would include the first column, then include the second column if it's not redundant, and so on. So if we have m vectors in a list of vectors, and if one in the list is a linear combinations of the one that come before, so vi, in the example above, this would be v3, the third column, is a linear combination of v1 and v2, we say that it is redundant. If we have a group of vectors where none is redundant, then we call them linearly independent. So none of them, or no combination of any vectors, can yield one of the vectors in this list. And finally, to define what a basis is, if we have vectors v1 through vm, and if they span a subspace, so this means there's enough vectors to go everywhere in the subspace, and that's condition one. And secondly, they are linearly independent, so none of them can be found using the others, then they form a basis of the subspace. Basically, we can say that the vectors v span, that means there's enough vectors to go everywhere in the subspace, but they are independent, so they are not too many. So there's enough, but there's not too many. And that means there is just the right number. Okay, span means there's enough, linearly independent means there's too many, and basis means there's just the right number. So in the example above, with v1, v2, v3, v4 in matrix A, we can say that v1 and v2 are linearly independent, v3 and v4 are redundant, and v1 and v2 form a basis of the image of A. No matter what we do with matrix A, the output will be a linear combination of v1 and v2. Exercise. Are the vectors here linearly independent? Well, there's a trick we can use when we have large vectors like that. It's not always obvious, but we can see there's a lot of zeros, and the first place we should look is this row here. v1 has a 0, v2 has a 0, v3 has a 0, and v4 has a 1. What that means is there is no way I can make linear combinations of these three vectors to get v4, because no matter what I do, I'll never be able to have a 1 here using 0 times something, 0 times something, 0 times something. So v4 is linearly independent. And then we can backtrack a little bit and notice that where v1 and v2 have a 0 in row 2, v3 has a non-zero value. And with the same logic, we can say therefore that v3 is linearly independent from v1 and v2. And finally, because v2 has a 0 and v1 has a 4, we can say that these two are linearly independent, or v1 is linearly independent from v2. So we've managed to eliminate the fact that v4 would be redundant. It's not. v3 is not redundant from the first two, and now we've noticed that v1 is not redundant. It's linearly independent from v2. So the last question we might wonder is in fact v2 redundant? And it's a good question, but since there's a 0 here where v3 has a 5, and a 0 here where v4 has a 1, and a 0 here where v1 has a 4, in order to build v2 using the other three, we would actually need zeros to multiply v1, v3, and v4 by 0. This would be the only way that we are sure there's 0, 0, 0. And if we do that, clearly we will not get this vector v2, because we will get the 0 vector. Secondly, do these vectors form a basis of Rn? The answer is no. Of R6, sorry. The answer is no. This, I think, is quite intuitive. If we have 6 dimensions, we need 6 vectors to span such a space. Are the vectors 1, 2, 3, 4, 5, 6, and 7, 8, 9 linearly independent? The question we ask is it possible to do A times V1 plus B times V2 equals V3? So can I have a combination of these that gives me V3? Because clearly V1 and V2 are independent. There's no way V1 can be multiplied to get V2. So the question is immediately, is there a linear combination of V1 and V2 that gives me V3? And we would see that yes, if I take negative 1 times V1 plus 2 times V2, I get V3. So they are not linearly independent. We could say, if we were looking at searching a basis, that V3 is redundant, or a span V3 is redundant. On the calculator, how would you do that? A V1 plus B V2 equals V3 can be written with this matrix. Here we are actually looking at, is there A times 1 plus B times 4 equals 7, A times 2 plus B times 5 equals 8, A times 3 plus B times 6 equals 9. So it corresponds to this matrix. REF gives this answer, and we would see, oh, A equals negative 1 and B equals 2. So not linearly independent. Okay, 2 theorems are going to wrap up this lesson. The first one is, consider M vectors in Rn. The following statements are equivalent. This is quite common in linear algebra, that we have statements that are all equivalent with each other. The first 3 are actually equivalent by definition. V1, Vm are linearly independent. None of them is redundant. That's by definition indeed. And V1 through Vm, there is no one that is a linear combination of the others. This is the definition of being redundant. So 1, 2, and 3 are equivalent statements for sure. How are we going to show that statement 4 and statement 5 are also equivalent? We're going to work specifically with the first statement here. We're going to show that 1 is equivalent to 4, and then we'll show that 1 is also equivalent to 5, and that will make all the connections. So for 1 equivalent to 4, we're going to do it in 2 directions. We're going to show first that 1 implies 4, and then we will show that 4 implies 1. And this double arrow, if you want, this double implication proves that 1 and 4 are equivalent statements. So let's just look again. V1 is V1 through Vm are linearly independent. So we're trying to show if 1, then 4. This means we are assuming V1 and through Vm are linearly independent. We assume V1 through Vm are linearly independent. The kernel of the matrix we could form with these vectors is made of all vectors such that V1 through Vm times x1 through xm is 0. That's the definition of the kernel. If we actually proceed to making this multiplication, we get x1 times v1 plus x2 times v2 all the way to xm times vm. So how could we solve this equation? Well, the only solution is if we choose x1, x2, x3 equals 0. And that is because we know these vectors v1, v2 through vm are linearly independent. So there is no combination of 1 that would give us the others. The only way for this to be true is if all xi's are 0. And so the kernel of the matrix is 0. Now let's do it backwards. We're going to first assume that we know the kernel of the matrix is 0, and we will try to prove that these vectors are linearly independent. We assume that the kernel is 0, and because of that, the equation x1 v1 plus x2 v2 etc. is equal to 0 has only one solution, and that is x1 equals 0, x2 equals 0, etc. xm equals 0. And therefore, the vectors vi are independent. We're pretty much exactly going backwards through our first proof. This x1 v1 comes from the fact that we know that the kernel is 0, so this equation here has only one solution, which is the vector 0 basically. Finally, we want to show that statements 1 and 5 are equivalent. The vectors v1, vm are linearly independent, and we want to show that is the same as to say that the rank of the matrix is m. So if v1 and vm are linearly independent, this is the same as saying that RREF has a leading one in each column. That is explained by the fact that we want to have no free variable, or else there would be ways that these vectors are not linearly independent. We could express one with the other. And if there's a leading one in each column, and we have m columns, as you can see, that automatically means that the rank is m. So this proof goes backward very easily to show that 5 is the same as 1. Lastly, a proposition: if v1 through vm forms a basis of a subspace, and v is a certain vector in the subspace, then there is only one way to express v. That is a very precious proposition. It means that if you have a basis, then you can only reach that a certain vector using one linear combination in the basis. So because we know that v1 through vm is a basis, that means there's at least one way to reach a vector v, because the definition of a basis is that it spans and it is linearly independent. So because it spans the subspace, there's at least one way to reach vector v. Now we're going to make this proof using a proof by contradiction, and we're going to assume that there are actually two ways to reach vector v, two different ways to reach vector v. So if we assume that that is true, we can list the two ways to reach vector v. We can say that v is a1 times v1 plus a2 times v2, etc. But it's also b1 times v1 plus b2 times v2 plus etc., where a1 and b1 would be different. These a1, a2, a3 and b1, b2, b3 would be different. By subtraction, we can see that v minus v is 0, and then this minus that is a1 minus b1 v1, and so on. Term by term, we can reach this expression. Now, again, referring to the hypothesis that that v1 vm is a basis, it means that v1 vm are linearly independent. If they are linearly independent, what is the only solution to this equation? It would be that every factor in front of the vectors is 0. a1 minus b1 has to be equal to 0, a2 minus b2 has to be equal to 0, and so on. But what does that mean? It means that a1 is equal to b1, that a2 is equal to b2, etc. So the two ways which we had declared as being different, we now discover that they are the same. It contradicts what we had said at the beginning. And so the conclusion is there is only one way to reach any vector if you have a basis. That wraps it up for sections 3.2. Thanks for listening.